Hello guys, for this video you are going to learn everything you need to know about solutions and concentrations. But more important, you will learn also that actually this is not exactly a flower pot. Come on. So let's start from the question, what is a solution? A solution is an homogeneous mixture of at least two components, which are the solvent and the solute. Why we use the word at least two components? That's because in solution you can have more than one solute. For example, you can have, I don't know, sodium chloride, or even put something like calcium chloride or other salts, and all of these salts in the same solvent. This will be anyway a solution, but the basic solution is formed by solvent and solute. Generally the solvent is the major amount and the solute is in minor amount. Some solutions can be made also by two solvents, but one of these solvents can be considered a solute because will be in minor amount. So keep in mind this definition, and let's see now some example. I put this example here. In this volumetric flask we have water, which is pink because we put inside this water some potassium permanganate. Potassium permanganate is violet solid, but as you can see from this volumetric flask, on the bottom of the flask you have some solid which is not dissolved. This is not a solution. Why? Because it's not homogeneous solution. You have really to keep in mind and to remember the word homogeneous when you are dealing with solution. This is a saturated solution, which is another concept. I will cover this part likely in future videos. Saturated solution is anyway a solution which you put an excess of salt, for example, in this case is potassium permanganate. You put an excess and the solvent is not able anymore to solubilize everything, so you will have something on the bottom which is something undissolved. Let's take also another example. This is a separatory funnel which is used for extraction, okay, but let's use it now as example for a solution. Here on the top we have water, and we have also another layer which is organic layer, and it's chloroform. Now chloroform is more dense than water, so you will see it on the bottom of the separatory funnel, so it will be the first layer. This is not again a solution because it's not homogeneous. Solution should be something like you cannot recognize which is the solvent and which is the solute anymore, because they are well mixed together. Let's see another example. We have this time oil, for example, and water. This is very common thing you can also see in the kitchen if you cook sometimes. So we have oil and water. Oil is on the top, water is on the bottom, and as you can see there are two layers. This is again not a solution because it's not homogeneous. You can distinguish the two layers and they are not miscible together. That's the reason why. So let's see what is a true solution. True solution would be, for example, even a solution we have seen before, so solution with water and potassium permanganate. This can be a true solution. The only thing is that we don't have to put an excess of potassium permanganate. This solution is made by water and potassium permanganate, and they are well dissolved together, well mixed together. You will see a pink, beautiful solution, probably purple even, but everything will be mixed, everything will be clear, okay, clear solution. And so finally we got a true solution. Now, keep in mind homogeneous for definition of solution, so you will have success for your examination. Now let's move on and let's try to understand what type of solution we can have. So we can have a solution which are called non-electrolyte solution. The solutions are not capable of conducting electricity. Let's do an example of this. Let's take our volumetric flask and let's take a solution, of course, made in this volumetric flask by water and sucrose. This solution is non-electrolyte solution because sucrose is made by neutral molecule. And this neutral molecule, which in the solid they have interaction, so they are all together, they make hydrogen bonding, and so they are all together and they form the lattice in the crystal form. However, when you dissolve sucrose in water, you will have that all these molecules will interact with water, and so they will be solubilized and they won't have interaction anymore one with another molecule of sucrose, but they will have interaction with water this time. So this is making then the solubilization, and this is making the solution in the end, which is clear solution and homogeneous solution. But this solution is not capable of conducting electricity because the basic molecule of sucrose is neutral. That's the reason why. So let's see what is electrolyte solution. Of course, it's the opposite, so it's solution which is capable of conducting electricity. And let's see an example of that. Well, the probably most famous example is with sodium chloride, which is the kitchen salt. The kitchen salt is made by sodium and chloroatoms. They are making the ionic bond when they are in the lattice. However, when you dissolve the sodium chloride in water, you will have first the dissolution of the salt in water, and then you will have also disgregation of sodium and chloroatom into sodium cation and chloride anion. This is because it's ionic solid, and so it's releasing in solution ions. This means that you have charged particles in solution this time, and this is a solution which is capable of conducting electricity. So these are the two types of solution, but electrolyte solution can be divided again into type of solutions. So in total we will have three types of solutions. So let's see how electrolyte solution can be also divided. We can have strong and weak electrolytes. Okay, so some electrolytes are behaving in a strong way and some electrolytes in a weak way, but not as in this picture. Let's see the true sense of that. Let's take again the kitchen salt, and in water this solid can be disgregated in sodium cation and chloride anion. And the way the sodium chloride will dissolve will be that all the solid sodium chloride will be dissolved in Na plus and Cl minus. And you won't have anything of the solid left in your flask. And so this is the concept of strong electrolyte. So it's called strong because everything will be dissolved, everything will be solubilized. But what happens with weak electrolyte? Weak electrolyte are, for example, the acetic acid. Acetic acid is a weak acid. So when you put this in water, this acetic acid, it will disgregate in CH3CO minus and one proton. One proton will be given to the water to form the ACE3O plus cation. So this reaction, as you can see, is written with two arrows because not all the acetic acid is completely dissociated in its ionic forms. So we will have in the flask some CH3CO minus, some H3O plus, but also some CH3COOH, which will be left in the flask. So in this case, we have an equilibrium. This means that some CH3CO minus is coming back and forming again the acetic acid. So it's equilibrium. So basically, strong electrolyte is completely dissolved and weak electrolyte is not completely dissolved in solution. That's the basic of that. So let's move on to the concept of solution composition. Solution composition means how the solution is made in terms of quantity. And this concept is related to the word concentration. So what is concentration? If you remember, solution is made by solutes and solvents. With word of concentration, I want to know how much solute, so the amount of solute I put in how much solvent. So I want to quantify both the solute and the solvent, and I want to be precise. I want to tell people I did this solution which is made by X amount of solute and X amount of solvent. I want to be very precise, and I want them to know how I did this solution, and I want them to repeat even. I want them to be able even to repeat my experiment. So it's something which has to do with precision and quantification. So how this quantification is made? Is made using these quantities: mass, volume, moles, and equivalents. But why I put this with different colors? This is because mass and volume are known as the physical quantities, which are also used in physics, for example. And moles and equivalents, they are chemical quantities. They exist all in chemistry, come on. And so if you keep in mind this, it will be more easy to go now to the next step of this video, in which we will learn the most difficult part. We have to learn the equations and definitions of this concentration. So let's start with concentration, which are expressed with physical quantities. We have two types of them. One is the mass percent. Mass percent is described as mass of solute divided by mass of solution times 100. And volume percent is similar, is volume of solute divided by volume of solution times 100. Generally, the mass percent is used when you have a solid solute, and the volume percent is used when you have a liquid solute. But let's try to understand with examples what they are. So let's take, for instance, a Erlenmeyer flask with water inside. Let's say we have 100 grams of water, and then we have sodium chloride, let's say 20 grams of NaCl. So let's say we have solution which is made by 100 grams of water and 20 grams of NaCl. We prepare it, okay? We just took 100 grams of water and then pour inside 20 grams of kitchen salt. So what is the mass percent of this solution? How we can find the mass percent of this solution? So the mass percent will be given taking into account this equation. So let's write it. Mass percent equals 20 gram of NaCl, because it's our mass of solute, so NaCl is our solute, okay? Divided by 100 gram of water, which is our solvent, but Consider that here we have mass of solution. So we cannot write only the solvent. We have to write the solvent plus the solute, which is the meaning of solution. No? Remember, solution is made by at least two components, which are the solvent and the solute. So we have to write 100 grams plus 20 grams of NaCl, so times 100. Then this is equals to 20 grams divided by 120 grams times 100, and if you do your maths, you will see that is 60.7%. So it's very simple. You have just to follow what is written here and to put the solute on the top of this equation and put solution on the bottom. So what is now the volume percent? To know that, let's take a common thing. Let's see a glass of beer, for example. So you take a glass of beer in your pub, and you see that is written there, this beer is 6.2% of alcohol content. Actually, this is volume percent of ethanol in the beer. So what does it mean? So it means that this volume percent equals to 6.2 milliliter of ethanol divided by 100 milliliter of solution times 100. This is actually the meaning of that. This means that this beer is made with 6.2 milliliter of ethanol, which are inside 100 milliliter of solution. Now, what is this? How this solution is made? Where is made by ethanol, water, and all the other ingredients you have in the beer. So it's very complex solution. Okay, in this case. So with physical quantities, we have two concentration, the mass percent and the volume percent, and they are all expressed with mass and volume, which are physical quantities. Now, there is also another concentration, which is a mixture of both, and this is mass volume percent. This is equal to mass of solute divided by volume of solution. Of course, times 100 as usual. So now with physical quantities, we have mainly three concentration. The most used one is these two you have on the top. This one is not so popular, okay? It's used only for physiological solution. Now, take in mind that mass of solute and mass of solution can be expressed with grams or even with kilograms. We don't care. The only important things to remember is that you have to put, for example, grams here and grams here. Okay, you cannot put top grams and then on the bottom you put kilograms. This will be incorrect. So please pay attention to unit of measurements, which have to be the same. And the same will be with volume. You can use whatever you want. You can use milliliter or you can use liter. The only important thing is that you put milliliter on the top and milliliter on the bottom, or liter on the top and liter on the bottom. Regarding mass volume, we won't have the same units this time, because on the top we will have grams and on the bottom we will have milliliters. In this case, it's important to keep the same proportion. So if you use grams on the top, I have to use milliliter on the bottom. And if I use kilograms here, I have to use here liters. So just take this into account, please. So we have done the first step of concentration. We have covered the physical quantities. But now let's move on. Let's move to the chemical quantities. So, what are the concentrations which are expressed with chemical quantities? Well, we have four of them. Let's start with the first one, which is mole fractions. So, the mole fraction of a solute, for example, is expressed as the mole of solute divided by the mole of solution. This means that we have mole of solutes on the top, and on the bottom we have a mole of solvent plus mole of solutes. We can have the mole fraction of the solvent as well, and it can be expressed in a similar manner as the mole of solvent this time over the mole of solution. And again, this is equal to mole of solvent divided by mole of solvent plus mole of solutes. Those are the mole fractions. Now keep in mind the mole fractions, as the name is telling to you, is a fraction. So this means that I can use one of them to calculate the other one as how. So 1 minus x solute equals x solvent, and 1 minus x solvent equals x solute. How this is possible? Well, because this is fraction, so it's the same concept of fractions in math. Let's do a simple example. It was done plenty of time in primary school. Let's be back to primary school now. Let's take a pizza and let's divide it in 8 slices of pizza. Now let's say that someone took 1 slice of that. So we have some pizza which is left. How to know the amount of pizza which was taken? We have to remember that we have only 1 pizza, right? And 1 pizza is the whole number. So 1 minus the 7 slices which are left over 8 equals actually the amount which was taken. But also 1, we can write 1 as 8 over 8, because 8 over 8, 8 divided by 8 is equal to 1, so it's right to write it like that. And so let's write it. 1 minus 7 over 8 equals 8 over 8 minus 7 over 8, which is 1 over 8. It's very simple, that the amount which was taken was only 1 slice, okay? And this is what we have done here. It's the same thing as this pizza, okay? So if I want to know the mole fractions of solvent and I know the mole fraction of solute, just do 1 minus the mole fraction of solute and you will get your numbers. That's the same, of course, if I know the molar fraction of solvent and I want to know the mole fractions of solute, okay? It's very, very simple. It's basic maths. Now, let's move on to the next concentration. This time, what we have? Well, this time we'll have the molality. So what is molality? Molality is expressed with lowercase m and equals to the mole of solute divided by the mass of solvent in kilograms. This concentration is an exception because this is the only concentration which has solvent on the bottom. All the concentration we have seen before and also we will see after will have solution on the bottom, okay? So this is really unique one, okay? Molality is unique concentration which has the solvent on the bottom. Keep in mind that for molality you have to remind the unit of measurements, because on the bottom you will have to put kilograms, okay? So kilograms, not grams, not milligrams, please, kilograms, okay? Mole on the top and kilograms down, please. So let's do an example to understand molality better. So let's imagine we have our Hermès flask as usual, in which we have our water. And then we have also 50 grams of KCl that we pour inside this 950 grams of water. So how to calculate this molality of this solution? Well, just keep in mind the equation. So we have to calculate the mole of solute. Mole of solute, as we know in chemistry, is the mass divided by the molar mass of that compound. So in this case we have to know the molar mass of KCl, which you can take from the internet or calculate it from the periodic table. So actually the mole of solute will be 50 grams divided by 74.55, which equals to 0.67 mole. Now we have everything to calculate the molality. So molality is 0.67 mole divided by the mass of solvent, which is 0.950 kilograms. I wrote this in red because you have to put this in kilograms, okay? So this was written in grams, so just convert this divided by 1000 in kilograms. Otherwise, if you put this as 950 grams, you will do a big mistake. Not big mistake, but probably you won't pass your examination. So put it in with the right unit of measurement, please. And then you just do your maths and you can easily calculate this amount, which is 0.70 mole over kilograms. Now, please remember that also molality deals with the mass, and mass is not depending on temperature. So molality does not depend on temperature, does not change with the temperature. So it's very useful to use molality when we have probably some variation in temperature, and so if it's changing the volume, for example, then it's changing the concentration if the concentration depends on volume, okay? So we can use molality when we are working in an environment with some experiment in which the temperature is changing. Otherwise, probably we will use the next one, which is molarity. Molarity can be written with the symbol capital M or lowercase c, and equals mole of solute, again, divided by, this time, volume of solution, which is in liters. So let's try to understand better what is molarity and to know how to prepare solution with molarity. So let's take volumetric flask, which is used for preparing precise amount of volume. This flask has a line here on the top, which is indicated volume you reach. For example, if this is 1 liter volumetric flask, this line will indicate that you reach 1 liter. If it's 500 milliliters, this line will indicate that you reach 500 milliliters, okay? These volumetric flasks are used because they are very accurate with volume. So let's pretend we have 1 mole of sodium bicarbonate and 1 liter of, we want to prepare 1 liter of solution. So how to do that? Just we have to put some amount of water inside this flask, but we do not have to reach the top of the flask, so we don't have to reach the line, okay? Just put some amount of water, and then we will wait the exact amount of sodium bicarbonate, which correspond to 1 mole. So just convert 1 mole of this into grams, then weigh the right amount by the scale, and then we will dissolve this into our volumetric flask with the water. Then you can also use again the wash bottle to wash some salt which can stay on the wall of the glass, so wash everything, but be careful to not add a lot of water because we have to stay lower than this line. Then you have to stir this flask in order to solubilize all the sodium bicarbonate, and once all the sodium bicarbonate will be solubilized, at this point you can add the rest of water in order to reach the line. But be careful to how you decide that you reach this line. Why? Let's go to magnifies this part with the line. So let's magnify it. Since water is polar solvent, it will cling on the wall of the flask to form this meniscus. So you reach this line when the bottom part of this meniscus is touching the line, okay? So this upper part, let's say it's up, you cannot do anything, but you know that you reach the exact amount when the lower part is touching the line. So I hope it was clear. So since molarity is expressed with volume, and since the volume is changing by the temperature, this means that molarity depends on temperature, okay? So keep this in mind. Now let's move on to the next concentration, which is this time normality. So what is normality? Normality is very similar to molarity. It's expressed by the symbol capital N, and it's equal to this time equivalent of solute divided by volume of solution, which is expressed in liter again. So it's very similar to molarity. What is changing is that instead of mole on the top we have equivalence. So we have to understand what is this equivalence. But before that, we can say that normality is equals to molarity times N. So there is a relationship between normality and molarity. And what is this N? So N is a whole number, so 1, 2, 3 or 4, okay, and so on. This means that normality can also be the same of a molarity if N is 1, or can be double or 3 times the normality and so on. So let's take for example hydrochloric acid. Now if we have concentration with hydrochloric acid, which is for example 13 mole over liter, so it's 13 the molarity, then which is the normality of this solution? Well, in this case the normality will be also 13. So it's the same because N is 1. And why N is 1? Let's take the reaction of chloric acid in water. Chloric acid in water is giving rise to H3O plus and Cl minus. It's giving rise to some ions. But these ions have the charge which is just 1. And so this is our N. So N is actually the charge which is developed by the reaction of your solute in the solvent. So normality is something which is related to the reaction which is happening between your solutes in your solvent, okay? So it can be a dissociation of acid in water, it can be even dissociation of salt in water, or can be sometimes even some redox reaction. In that case, in the case of redox reaction, you have to take into account that N will be the total number of electrons. In this case, N, in the case of acid or in the case of salt, will be the total number of charge. In this case, the charge is 1 plus and 1 minus, so is 1, okay? Let's take another example in which this normality will be different from molarity. For example, let's take this iron salt. This iron salt is made by 2 iron cation and 3 sulfate anion, okay? So the iron is charged 3 plus and the sulfate is known to be charged 2 minus, okay? So what is the total charge number? The total charge number is 6 because we have 2 iron which are charged 3 times, okay? This means that 3 times 2 is 6. So we have 6 plus and then we have also 6 minus because 2 times 3 is 6 again. So we have to take the total number of charge of the balance reaction, okay? So it should be balanced, otherwise you will do a mistake. So N is 6. So now let's say we have 1 gram of this iron salt. We want to calculate the normality of this solution, which is made by 1 gram of this iron sulfate 3 in 1 liter of solution, okay? So to calculate the normality, we have to know what is equivalent, and we know already that the solution is 1 liter, so this is not a problem. The only unknown amount is equivalence. So before calculate equivalence, let's calculate the moles of 1 gram of iron sulfate, which as we know is made by mass divided by molar mass. So it's 1 gram divided by the molar mass of this iron salt, and everything is equal to 0.0 0.0025 mole. This is the mole of this salt. Now we need the definition of equivalent. So equivalent is given by the mass of solute divided by what is called equivalent weight. Now the equivalent weight is given by the molar mass, which we already know, divided by N. Okay, so it's just the molar mass of your solute. In this case is our iron sulfate divided by N, so N is 6. Okay, so equivalent will be 1 gram divided by 399.858 divided 6, which is equal 0.015 equivalents. So now we know the equivalents, and since, as you can see, 1 gram divided by 399.858 is the same we have here, and this is actually the mole we have already calculated, this means that there is a relationship between equivalent and mole, okay? And this relationship is that equivalent equals mole times N. So we have now two expressions for find equivalence. One is mass of solute divided by equivalent weight, and you need to remind what is equivalent weight, which is molar mass divided by N, or more simply, you can just remind that equivalent is actually moles times N. Okay, it's more simple to remind this one than this one, but probably in your examination they can ask even for this one, but I will use only this because it's simpler. So now we know what is equivalent, so we can even calculate equivalent just by multiplying the mole times 6. Okay, it will be the same number we have already obtained here. So just take mole times 6 and you will gain the same number. Okay, now we want to know what is the normality of solution made by 1 gram of this iron in 1 liter. So we have 1 liter of final solution in this flask. So what is the normality of this solution? It's very simple. We have already the equivalents, so it's this equation here, so we have the equivalents. We have just to divide by the volume, but the volume is 1. This means that this is our molarity actually, so 0.0025 is the molarity of this solution, because molarity is mole divided by the volume, okay, but the volume is 1, so this is also our molarity and this is our normality, okay. And as you can see, there is the same relationship between molarity and normality. So as you can see, normality is higher than molarity, okay, because it's molarity times 6, as we have already said here. So this is the concept of normality, is slightly more complicated, but normality is not very used in chemistry, but probably you have to know that because during examination it will be for sure asked. So now let's do a recap of everything we have seen in this video. So first we have given the definition of solution, and we have said that solution is mixture of at least 2 components, solvent and solute, and this mixture is homogeneous. And we have said that this word is very, very important, okay? Then we have seen different types of solutions. We have seen that there is non-electrolyte solution, which is incapable of conducting electricity. At the same time, there is also electrolyte solution, which is the opposite, and electrolyte solution can be divided into strong electrolyte solution and weak electrolyte solution. And we have done the example of sodium chloride and acetic acid, which is weak electrolyte and also sodium chloride is strong electrolyte. Then we move to the concept of composition of solution, and we have said that composition of solution is the quantification of solution, and it's related to the word concentration. And we have also said that there are several kinds of concentrations, and these concentrations can be divided into two categories depending on the units we use for their definitions. So we can use physical quantities and also chemical quantities. Regarding the physical quantities, we have two main concentrations. One is the mass percent, which is expressed as mass of solid divided by mass of solution times 100, and volume percent, which is volume of solid divided by volume of solution times 100. So the physical quantities are expressed with all mass or with all volume, and they are percentage. We also have said that you can use the unit of measurement that you want. The only thing is that you have to be coherent with them. So you can put grams here, and here you have to put again grams, okay? Or kilo and kilo again on the bottom. You cannot put gram and kilos, gram on the top and kilos on the bottom. It's incorrect. So then we have seen the chemical quantities. The first concentration expressed with chemical quantities is molar fraction. We have, for example, seen the molar fraction of solute, which can be expressed as the mole of solute divided by the mole of solution. Then we have also seen molality. Molality is mole of solute divided by the mass of solvent in kilo. Then we have seen molarity, which is again mole of solute divided by the volume of solution in liters. And then normality, which is equivalent of solute divided by volume of solution. So to remind all this concentration, you can divide it as I have done in physical quantities and chemical quantities. The physical are expressed only with mass or only with volume. And then you can remember the chemical quantities. Remember that you have to use mole, okay, or equivalents on the top of the equation. And all the time on the top you have solute. Or in one case, when you want to describe the molar fraction of solvent, you will have solvent on the top, but this is only the one exception. You have to remind that molality is very different from the others because it's the unique one to have solvent on the bottom of the equation. All of the other have solution. So I hope these tricks will help you to remind this concentration. Otherwise, just practice with them and you will remember them. So with this, I would like to close and bye bye.